Hello and welcome back to Calculus 1, section 5.5, u-substitution. And this is one of those sections that you, if you know it, you are welcome in Calc 2 class. If you don't know it, don't bother. All right? Technically, this is going to be the integration technique, and about 90% of integrals you ever do in all of the courses from this point on will be this. Because this particular u-substitution method for integration is backwards chain rule. We all know that vast majority of derivatives are chain rule, therefore, right, common sense would be that the vast majority of integrals should be backwards chain rule, which is what this section is all about. There are a number of ways to derive the formula for this and so on. It clearly involves function composition because it's backwards chain rule. The whole idea is to figure out something that I'll outline in a great detail called function derivative pair, and then set the function to be u, and then go from there and solve the problem. Now, before I write any formulas and things, let's just think about the need for something like this. So if I have to integrate, let's say, x plus 3 dx, we know that I can just go in and integrate each of these terms independently and get x squared over 2 plus 3x plus c and be done with it. The next integral would be the same x plus 3, but this time I'm going to square this, and we know that we can still do this because we covered right in 4.9 where you square this, so you FOIL the whole thing, you get x squared plus 6x plus 9 dx, and then you integrate each one, getting x cubed over 3 plus 3x squared plus 9x plus c. So we had a problem that was squared, and then you square it, actually, right? You FOIL, and you can integrate again term by term. Well, now the hell breaks loose if you have x plus 3 raised to the 13th power. So what now, right? Yes, you can go on and FOIL, and I'll wait. But since the final is tomorrow, right, there's no time to FOIL this all the way to the 13th power. So let's think about an alternative approach. So this is what we are learning today. I will say, I know how to integrate, so let me write it here in blue. What I know how to do is x to the 13th dx, right? So that's what I know. But I don't have that. So let me make this thing over here into x, but x is already used, so I'm actually going to make it into a different variable. I'm going to call that variable u. So if I am able to make this into a u, I would just have u to 13th, and that's u to the 14 over 14. Easy to integrate, right? So I am looking at the problem, and this is going to be for all the problems that are following this one. I'm going to look at the problem and I say, oh, if this was just, right? It's like the well-wishing. You all know that you all have great plans on how to spend like $1 million, right? You know exactly what to do. If you were to find $1 million, you're all set because you know what to do with it, right? Well, this is the same thing, right? You would just say, if I could only have so and so, I would be able to do this problem easily. And in most cases, that is your u-substitution. So my, wishes over here are to have this x plus 3 to be a single variable so that I can just have that single variable to 13th, which is a joke to integrate. Well, let me make then u equal to x plus 3. Right, if I make, I'm going to put these in red. So let me make this x plus 3 to be u. Right, so that's me just trying to fix the problem so I can do it, right? Now, the thing is that this over here, right, the dx part is not there for decoration, right? You know that that's the width, and that one is in terms of x, right? And you are trying to change your problem to be in terms of u. So when you swap your function, you have to swap also dx, because you can't be integrating u to the 13 in respect of dx. That makes no sense. All of the variables have to be the same, right? So your job now is, once you switched this part into u, you also have to switch the other part, dx part, into du. And you achieve that by simply differentiating your u substitution. So that will be du dx is equal to 1. From where you can solve for du by moving dx to the other side. And now we see that du and dx are the same. Now, this is going to be only the same when you have a linear problem, which is extremely rare. Most of the time, this du-dx relationship will be more complicated. But essentially, this is it. This is what you do, right? So you look at the problem and you say, oh, if I could just have so-and-so, and then you go for it with the u substitution. And then you transform your dx into du, and you're done. So now when I substitute things, right, the x plus 3 becomes u, so it's u to 13, and dx is du, and there we go. The whole problem from up there became much easier. And now all I have is u to 14 divided by 14 plus c. Now we have to go back into x variable, right? Because x variable is the one that was in the original problem, right? Not u. So you have to remember to put back x. So it's 1 over 14 times x plus 3 to the 14 plus c. Right? There's a sentence that you can quickly chant every time you're done with this problem to remember. I don't care about u, I care about the x. Because that's, right, you make sure that x is back, right, because u variable, right? So I don't care about u, I care about the x. Now, where would we be if we wouldn't check this, right? Because we care, right? We genuinely care. So we want to make sure that our answer is good. All you need to do is to differentiate that answer, and hopefully, right, if you get the original x plus 3 to the 13th, you did the problem right. If you don't get it, well, something is wrong. So I have 1 over 14 times x plus 3 to the 14th plus c in a derivative, right, to check. And over here now I have, I copy the constant, then I drop 14 down, and I have x plus 3 to the 13, and then I have plus 0, the 14 cancels, 14, and there it is. It's x plus 3 to the 13, so it's good, right? So you should be doing this on your exam, right? Checking the problem to make sure that, the biggest issue now of this class, obviously, is you're going to have very little experience till tomorrow with the most important integration technique. But the good thing is that the Calc 2 is not starting in like another 10 days, so you can actually get a mini PhD in that if you spend ample time on YouTube and with the textbook to get ready. Let's take another example. How about the integral of sine of x minus 5 dx, right? So this is another example. And you say, well, okay, if this x minus 5 was just one thing, I know how to integrate sine of the one thing, right? You know how to integrate sine x. So we can immediately say, let u be x minus 5. And that should be obvious, actually, because it makes problem to be sine u, and you know how to integrate sine u. Du is again equal to dx, Let's do one more time. So du over dx, right, as you differentiate in respect to x, you will get 1, and then du equals dx when you kick dx to the other side. What you get now is integral of sum sine u du, which is negative cosine u plus c, and then I don't care about u, I care about the x, which means cosine of x minus 5 plus c. And we move along. Right. Now you have memorized the integral of e to the 6x dx. Right? You all know what the answer is. Or if you didn't know, you know it after the exam last time, right? Because it was on the exam, except it was e to the 3x on the exam, and now you have e to the 6x, right? So when you're looking at this, you know that the answer must be e to the 6x divided by 6 plus c. But I asked you to memorize that in 4.9, so you are able to do your homework. Now we actually learn how to do that. The only thing that you actually know is how to integrate e to the x. So let's make this 6x into just one variable, and we'll call that u, right? So u is 6x. And now if you differentiate, you get du over dx is equal to 6, from where du is 6 dx. All right. So now this is a little bit different than before, because I don't see any 6 times dx, right? And there are two ways to deal with this. If dx from the problem and dx from the substitution differ by a constant, you can fix that by multiplying the constant and 1 over the constant in front, which will give you enough building blocks to do the substitution. So what happened? Well, if I am to do the substitution, oh, come on, pen. So if I am to do the substitution here, I clearly have integral e to the u, right? That's given. Now the problem is that my dx and the dx from the substitution are not the same, because this one is missing 6. And there are two ways to deal with that. My preferred way, which does not have to be your preferred way, is to fix it by multiplying by 6 and dividing by 1 over 6. In which case, clearly you have 6 dx to make a du over here. Right? So that's my preferred way. Now there's other way that I'm also going to show you now, and then you pick what your favorite poison is. Now, if you observe, there's that 1 over 6 that has to go in front of the integral over here. Just need to move that integral. So this 1 over 6 has to be copied. So I copy red 1 over 6. So both 1 over 6 and 6 is what I put in to make sure that I am also satisfying the du switch over there. So now when I have 6 dx, well, 6 dx becomes du, and then 6x becomes u, so we have e to the u, and then du. And then I copy 1 over 6 because that has to be there. Now when you integrate this mess, you get 1 over 6 e to the u plus c. I don't care about u, care about the x. You get e to the 6x over 6 plus c, exactly what you're supposed to get. But now you see the process behind memorizing the formula for sine of 3x and cosine of 5x, right? You all know that they're all divided by a. This is why, right? This is why, because they will all have this piece, and you always have to fix it with the other part. Now, this is one way of dealing with constants that have to be fixed. Let me do a cosine problem where we also have to fix the constant, but I'm going to fix it in the other way, and then you pick whatever you like better. So then you pick what you don't like and use the other one. How about that? So cosine of 8x dx. This problem suffers from the same issue, right? Oh, if I just had cosine x, right? So let me use the substitution u equals 8x to fix that. And then du immediately is going to be 8 dx. You quickly learn that you just take the derivative and you put the dx on the right. That's going to hopefully be second nature on a problem number 3 when you do it. All right, so now I'm looking at this and I can start substituting, right? So I have cosine of u, but now I don't have 8 dx. Well, the other way is to actually solve for dx here. And you get du over 8. So you plug in du over 8. Now we know that for integrals you can kick constant outside. So here's your 1 over 8 cosine u du, which is 1 over 8 sine u plus c, which is sine 8x over 8 plus c. So that's another way, right? You can actually solve for dx because you need to substitute that as well. So you substituted this and you substituted this with the two formulas that are, as you can see, 8x is u and dx is du over 8. So you just plug them in. This is what it's called substitution method, right? You are substituting one expression for another. All right, so let's see how you fare. How about the integral of x, and then we have x squared minus 3 to the 6th power dx. This is a tag trick here, but you might be able to pull it off. After this, I'm going to write the formula, and then we're just going to do another 6,000 examples. What do you think u should be in this case? X squared minus 3. Okay, so go from there. So u equals x squared minus 3. Might happen, yes.
Is there anything
I don't know if I have it. I should have it. If I drop it off in my office, then I don't. Let's see. I have a bunch of stuff. Okay. Patrick. Patrick, and you're right? Ali still?
Yeah.
Yeah. Do we have to fix a constant in this case? Anyone? Yes or no? Yes, we have to fix a constant. Good. The derivative of x squared is 2x, and we only have x, right? So, du is 2x dx, and as you can see, I don't have the 2 that I need in front of x to make it 2x dx for a substitute. So you can place a half in front and 2 inside, which is my favorite way of doing things, or you can say, well, I have, so you don't fix anything, you say I have x dx, so x dx is equal to du over 2. I don't care which way you do it, just do it, right? So either way, you are going to have, when you substitute, 1/2 integral, 2x dx is going to be du. The entire guts of the parenthesis is u, and you have this 6th power on top of u, right? So 2x dx, so 2x dx is du, right? And x squared minus 3 is u, if we color code this. So now, when I integrate, I have 1/2 u to the 7 over 7 plus c. This is further 1 over 14, and then u is x squared minus 3 to the 7th power plus c. So generally, silly way to lose the points is to forget to write the 7th power. That's generally what happens. Other than that, I mean, if you know what you're doing, you should be scoring well on these problems. And as I said, guys, this should be the thing that you practice the most of everything, not just because there is a final tomorrow, but because there is a Calc 2 class coming up. Obviously, if this is the end of your math education career, then you just take off tomorrow and show up for the final. You just need that C, right? Because, no, everyone won't say? Great. That's the spirit. Let's just write the formal formula for u sub and just discuss it for a few moments. So integral of the function composition times the derivative of g, right, is equal to not integral, it's equal to the antiderivative with g plugged in, plus c if you want to. So this is the formula for u sub. Now you said, well, I don't see u. Why? What is this called u sub? I don't see u. Well, u is in here. The formula that is given in the book says integral of f of g of x times g prime of x dx is equal to integral of f of u du, where u equals g of x. So this is the formula that is given in the book. This is more as the process. They call it a theorem, but actually this doesn't solve it, because you still have to go and you don't know what the f of u is, right? So over here you see that you have the function and then you have the antiderivative. That's the solution, right? So when you write it in this way, this is the actual, right? That's the actual answer to the problem. So I modified a little bit this thing from the book. Now I need to direct your attention to two parts of this formula. There's this gx and g prime x. All right? We know that for every case other than e to the x, these are two different things. It's x squared and 2x. It's sine and cosine, right? So it's, and this is what I meant when I said function derivative pair. If you are able to find function and its derivative, that is your u du pair. And the rest, if this is a proper method for integration, the rest will fall in its place. So I have, for instance, I have a problem like this. Integral of x squared, the square root of x cubed plus 6 dx, right? And then I have a problem like this. The integral of square root of x plus 18 raised to the 4th power divided by square root of x dx, right? So if you're looking at these two problems, they all have a square root in them, right? So now, how are these problems different, right? Well, the trick to being successful in solving these u-substitution problems is in actually figuring out the function derivative pair. These two problems both have square root of x in them, right? But they are vastly different because the top problem has the u under the square root because x cubed has its derivative as x squared, where on the bottom the x square root of x plus 18 is u because the derivative of square root of x is 1 over another square root of x. See that? So this is where now u-substitution is becoming tricky, when we have more interesting problems that could go more than one way. Now, when students ask me, so how do you know? Well, obviously it's experience, like everything else in life. And I've been doing this for 15 years, so obviously I'm going to know, because I'm doing this every single semester, multiple times, in multiple courses for 15 years. How are you going to know? Well, you are going to sit down and just keep pounding on this until it becomes, again, right, something that you know. This is how we learn things in life. So that's that. You have to understand that a certain part of this is the experience and the sheer amount of problems and situations that you run into. Now, second part is, you have to think about these things, not try to match a problem to another problem that was done. Immediately start from the empty sheet and say, all right, on this page I have nothing other than a problem. What is my function derivative pair, right? Whatever the function is, that's u, and then the derivative will actually end up in du, and then maybe I have to fix a constant or not. So when I'm looking at the top problem, I'm ignoring this square root completely, actually, because my eyes are immediately fixated on x cubed and x squared because I know they're derivatives of each other, right? X squared is derivative of x cubed. Yes, there's a constant floating about, but we'll deal with that. And when I'm looking at the bottom problem, everything else disappears other than, wow, I have a square root in the denominator and I have square root in the numerator. I know when I take the derivative of a square root, I get a square root in the denominator. So yes, right? So to solve the top problem, we would use u equals x cubed plus 6, which gives me du to be 3x squared dx. And I see I have to fix the constant in this case. In the bottom case, I have u equals square root of x plus 18. That will give me u to the 4th. Now, look at the du. Du is 1 over 2 root x dx. Right? When you take the derivative of root x. Now, obviously, if you don't have knowledge of derivatives, if that is rusty or weak, it will get much harder to spot these things, and you would have to do trial and error. Now, what happens if you are running in straight line, you run into a brick wall? Well, you hopefully turn around and run the other way because you're not going to phase through it. You're not that fast. Just average at best. So what you are going to do is, if one substitution fails, you're not going to walk away, right? You're going to try something else, hopefully, because you want to learn this thing, because there's next 5 classes coming up, and they all have this as its core and the most important integration technique. So not if, but when you fail on the first try, you try something else, and you try something else, and eventually it will become clear which one of these methods and which one of these techniques actually works. So, you know, x cubed plus 6, well, okay, that's my function, that's my derivative for that function, so great, that works, right? Over here, the derivative of x cubed, you learn to ignore these plus a constant because they die in a derivative. So you learn to ignore that, right? But when you take the derivative of root x, you get 1 over 2 root x. And you say, oh, I don't have a 2. You put it there if you don't have it. Right? That's easy to fix. You're going to fix the constants. You're going to fix a 3 over here with the 1/3 in front, and you're going to fix a 2 over here. Well, then times 2, right? Because you put inside the integral, you put 1/2, right? Then you better put 2 on the outside. So be wary of those things. And if you're doing these things, you better have 2 colors. Don't write this in the same pencil, these 2s and 3s. If you write this in the same color, you might think that the problem was posed that way. No, it's not going to be, right? So if you don't have multiple colors right now, swap with the person sitting next to you with a blue pen or a black pen or a pencil and a pen, so you know that that's added later. It's not there in the original problem. These will stay as your challenge problems to solve at home. The top one obviously will just be 1/3 integral of square root of u du, which would be just a quick integration. And the bottom one will just be u to the 4th, even easier, right? So the bottom problem is actually easier than the top problem. It looked much worse to start off, but much easier to actually integrate. So, these are the two. Here, I'll put the instructions right there. All right. Now let's talk more interesting stuff. How about integral of sine to the 9x cosine x dx? This is actually going to be an introductory problem in chapter 7 in Calc 2. You'll have a different exponent here. So trigonometric integrals have their own section in Calc 2 in chapter 7, 7.3 to be more precise. So this will be the introductory problem with whatever exponent is here. Now, when you start having exponent here as well, and then you toss in all other trig functions, then that's actually the core of that section, right? But the introductory problem is actually studied now, because it's just a basic u sub. Do we all see function derivative pair? Do we? Do we? Do we? See, when you're looking at this, you are seeing trigonometry. What I see is a polynomial. Now you go, eh? And I say, yeah, because the derivative of sine is cosine, which means entire sine x is u, right? The next step kills trig completely, because this is actually u to the 9. When you do these problems enough, and I promise you this in Calc 2, the next day after 7.3, you would look at a problem like this and you would just say, oh yeah, the answer for this is sine to the 10th power over 10. You would just know it by looking at it without doing any work. Because it will be just, oh yeah, that's that u sub from Calc 1. Because, as I said, this turns into a polynomial. You have a function derivative pair of sine and cosine, and the function is your u. So u equals sine x, and du equals cosine x dx. I don't even have to fix a constant over here. This is great. The whole thing is just u to the 9 du. You see, sine x is u, so u to the 9, and a cosine x dx, the entire thing is du. So, u to the 10 over 10 plus c, as I promised, 1/10 sine to the 10x plus c. Go ahead, differentiate. You'll see it works. The chain rule will get you the cosine when you differentiate, because you're differentiating sine to the 10th power. That's 10, which cancels with a fraction, times sine to the 9th, times the derivative of the inside derivative sine is cosine, and there you go. Right? It's cool. So this is going to be revisited. Well, everything from this section will be revisited. Now let's take a look at another flavor of the integral of x cubed times sine of x to the 4th dx. Now, how is this problem different than the problem up there? What's our function derivative pair? Well, derivative of sine is cosine. I don't see it. So what's the function derivative pair? Just x to the 4th and x cubed. You see that? So this problem doesn't have a cosine, right? It still has sine, it still has x, it still has exponents, but there's no cosine. So it's different than the problem up there. And as I said, guys, you cannot learn this section learning this example by example, because the combinations are endless. What you have to achieve, and unfortunately achieve till tomorrow, because there will be one question with part A, part B for these things. One of them is, will be, because I still have time. One of these will be something with polynomials, you know, like the first few problems. And then something, then the second one will be something more exotic with ease or roots or trig. You cannot learn this example by example and then try to match. Break through right now and try to say, okay, he's talking about function derivative pair, and he said that 15,000 times. That is the safest bet. And again, if you're going to Calc 2, that's the way, all right? So what is the function derivative pair? Here, I'll write function derivative pair. Under function, I'll write x to the 4 because its derivative is x cubed. And that's what I need. Now, if I want to write function derivative pair for the top problem, I'll write sine x cosine x because they're both present. And please note that my u is always the f, the function, right? So the top part, u was sine x because that was a function, and then clearly its derivative, well, that's du because I'm taking the derivative of u. So now I have u equals x to the 4, and then du is equal to 4x cubed dx. And I see I am missing a 4, so I'm going to fix that. I need 4x cubed, but I can't just, put 4 out of nowhere. I have to balance it out. So that's your different color, because that happens later. And now I have 1/4 integral. Let's color code again. So we have this thing to be your du. So that's your du. And then you just have sine u. So integral of sine u, again, your f, your function, which was u, is x to the 4. So this is simply, the integral of sine is? Yes. Yeah, I was just waiting for someone to say cosine. I needed negative cosine. Cosine u plus c, which gives us negative 1/4 cosine x to the 4th plus c. Go ahead, differentiate, it has to work out. So I'm going to put two problems for you to practice. Then we're going to hit the break. When we come back from the break, part 2 of this lecture will deal with u-substitution with indefinite integrals, ones that have limits, and also a more exotic case of this called back substitution, which rarely pops up, but pops up. Yesterday, my Calc 3 class was like, oh, we forgot about that. And I said, yeah, I can tell. So here are the two problems for you to enjoy. Integral of x e to the x squared dx. So that's one. And oh, this looks problem 19. This was problem 18 and 19. Nice. Okay, 18 and 19. So 19 is integral of 2x squared divided by the square root of 1 minus 4x cubed dx. So you can see both problems. I have to leave space so I can fit the 18, so you can just... All right. You have 20 seconds. Let's go. No pressure. I'm just going to ask you to give me substitution over here. So what's the substitution, the top problem? X squared. So that will make du 2x dx. And you clearly have to fix it, right? How about the bottom one? 1 minus 4x cubed. Very good. Now that will make du negative 12x squared dx. So what do I need to multiply? Negative 6. Nice. So there has to be a negative 6 over here and negative 1 over 6 in front. Okay. So hopefully if you are stuck, this is enough to get you jump started. And keep pushing. All right, let's take a look at this. So the top problem, we can say that u is x squared so that we can get e to the u. We know how to deal with e to the u. And now we have 1/2 integral, color coding over here, right? 2x dx is going to be du, and I have e to the u. Integral of e to the u is e to the u, so 1/2 e to the u plus c, which gives us the answer of 1/2 e to the x squared plus c as the answer for that question. The one on the bottom looks much scarier, but it's not that bad. I have -1/6 integral of -12x squared, you can put dx there, divided by square root of 1 minus 4x cubed. So you see that the entire numerator is exactly du, so you have 1/6 integral du over square root of u. It compresses so much. I mean, the very intimidating problems become very easy after substitution. And please, when someone tells you, what do you know? Right? So now, -1/6 integral of u to -1/2 du. We add 1, so that's going to be +1/2. So I have -1/6 u to the +1/2 divided by 1/2. I put 2 on top immediately because double fraction would solve that way anyway. And I have the 2/6 that becomes -1/3. Square root of u plus c. Now, I don't care about u, I care about the x, which means we substitute 1 minus 4x cubed plus c, and there it is. Now, the skeptic in you would be like, I don't know. All right, fine. I mean, bring it on. Here. The derivative of -1/3 square root of 1 minus 4x cubed plus c, because we care. Copy -1/3. The derivative of this square root is 1/2, and then 1 minus 4x cubed to the -1/2 times the derivative of the inside, which is -12x squared, and then plus 0. So now I have negative and negative positive, and so this is -1/6 times -12x squared divided by the square root of 1 minus 4x cubed. So now this is 2x squared divided by the square root of 1 minus 4x cubed. Is this the problem? That's the problem. 2x squared, yep. See that? So it's good. All right, as I mentioned, there is going to be a part 2 for this lecture, so let's go for the break and then continue after the break.